What were we talking about? Oh yeah, we were talking about the homework, and I think it's important before we do anything else that we talk about the very last problem. And actually, I should say something uh, about, this homework is really, how do we say it? It's your first sort of introduction really to proofs, or I guess another way of saying it, will be the first time that I am going to be assessing sort of your ability to try to, learn the basics of writing a proof, which is really one of the goals of this course, is to get you not just exposed to it, but so to see some improvement as the semester goes on. So, you don't need to get worked up and overwhelmed about how you're doing things right now. You got to think of the beginning stuff sort of as a learning experience. So keep that in mind. If you still sort of feel overwhelmed with homework, number one. Nonetheless, let's pick up where we left off. So the last problem on that homework essentially said something of, it was more like an open question to you. So how many solutions does this equation have? And how do you verify that? So before you can even answer this, this is again a question that I'm posing to you, so that we can nitpick on what does this actually mean. So the first thing that we say is, when I say how many solutions does it have, the question you should ask yourself, whether you know the answer or not, is what does it mean to be a solution? So one way to think about that is as follows. So recall, we call, we could think about it as like this. We can think of it as a sort of set of, so maybe I don't want to use too much fancy notation. So we might say something like this. We call X, Y, and Z a solution if, when substituted in, the statement is true. So an obvious thing to note is the following. Note that X equals 0, Y equals 0, and Z equals 0 is a solution. It's a boring one, but it is a solution if you plug it in. You see that. And then another solution you might say is, okay, just by plugging and guessing, you might say X equals 0, Y equals 1, and Z equals 1 is a solution. So maybe we'll write it like this. So is this. So just by looking at this, we've actually found two solutions. And really there's more, because if you switch X, if X is 1 and Y is 0, then you get a solution. And so it doesn't take long to figure out that there's going to be some solutions. And by the way, I think I made this clear in the homework, and you should double check. We should say, this should say how many integer solutions. So if I go to the homework real quick, I just want to make sure I stated the problem correctly before I go any further. So bear with me. don't want to have any. Yeah, okay. So yeah, okay, so that's the way I stated it. So I actually stated it by saying how many solutions are there. So let's leave it like this. Now, another thing to think about is if you pick any two numbers for x and y, then you can easily solve for z. So in fact, this thing has how many solutions? How many solutions do we expect to have? Well, we expect to have infinitely many solutions. So note, another thing to notice. If you pick any numbers for x and y, then z is just, if you take the square root of this tells us how to obtain a solution.
Professor Ryan?
Yes.
So can we just imagine, or just tell that neither x nor y is dependent on z, but z is dependent on them, but x is not dependent on y and y is not dependent on x, and both of the arguments x and y is not dependent on z. So we can just put as many as numbers, integers, we can just put instead of x or y, so that we can have any z.
That's correct. I mean, so basically, so you're thinking about it in a correct way, and that's essentially what I'm writing here. It doesn't matter what x and y are. So the way I've written this equation now, I say z equals the square root. What that does, as you said, is it shows that x and y are independent of each other. But it does say that z depends on x and y. So another way of saying that is, thus, this guy, and by the way, there's an easier way to see this, which we haven't mentioned yet, but this guy has infinitely, whatever that means, many solutions, where x, y, and z are real numbers.
So when I looked at this problem first, it reminded me like y equal car x, just in terms of x is independent, like.
Well, right. I mean, the way if you go back to the original page, the way it's written like this, when it's written in this form, x squared plus y squared equals z squared, then all of these guys depend on each other, as it's written here. So what we call this equation here, we call this an implicit equation. But what happens is when we rewrite it like this with the z equals the square root, now this is explicit. Z explicitly depends on x and y. Now, another thing to notice, and maybe this is something some of you did, is this is just
Pythagorean theorem.
Yeah, that's exactly right. So geometrically, it's not just a Pythagorean theorem. This is a circle. All right.
Oh yes,
Or
radius.
if you want, yeah, the radius would be z. Or as you suggested, think Pythagorean theorem.
If x 0 and y 0 is 0, yeah, we can do that.
Yeah, so that's two ways to think about that. Now, that's not the only way to think about it. As I said, look, if you pull the homework up, and let me share this screen. if I share the homework, notice I said how many solutions are there to the equation, and then I said prove it. So the purpose of this particular problem is to actually get your mind thinking about, what do these words mean? What does the word solution mean? What does the word prove your claim mean? So one of the things that I'm doing here is I'm telling you, I say, okay, here's how I'm thinking about the problem. Maybe you thought about it differently. That doesn't mean you're wrong. Perhaps you thought of it differently and you are correct. The way I'm thinking about the problem is I first say, are there any obvious or trivial solutions? And the trivial solution would be everything equal to 0. And then there's also lots of trivial, anytime you set x equal to 0, there's a trivial solution for that. 1, 1, 2, 2, 3, 3, whatever. So there's lots of what we'd say trivial solutions. But then the question you might ask, once you start thinking about this as the Pythagorean theorem, you might ask, are there integer solutions? And here's an, and I didn't ask you to do this, but it's worth thinking about. There are actually infinitely many integer solutions.
3, 4, 5.
Right, that's the most famous one. So for example, yep, that's right. So the most famous one is a 3, 4, 5 triangle. So x equals 3, y equals 4, and z equals 5. And the solutions are called, they have a name. So integer solutions are called Pythagorean triples. So that might be something you want to be curious about. If you are, you're curious, you can Google it. It's not difficult to figure out how to get more of them. It turns out once you have one Pythagorean triple, any multiples of them is also going to satisfy the equation.
We can use, sine square plus the cosine square equal 1, or imaginary solutions for that.
Yeah,
In
no,
this,
yeah.
Of course, we have, like, integers, let's say float numbers, let's say imaginary solutions, all are infinitely many. But should we just, quote all of them? Like, we can just, just stress out the Pythagorean triples. That would be enough, and doubles of it, triples of them. That would be enough, I guess, isn't it?
Yeah, well, that's another way to think about it. So I was on purpose, this problem was sort of, you have to think about how I stated the problem. I stated the problem, I didn't state it specifically. I didn't say show that there's infinitely many integers. I posed this problem more as a curiosity to you. I said, how many solutions does it have? And so there are lots of correct ways for you to think about this problem as it's stated in the homework. And that's the purpose of it. I'm not looking for some specific solution necessarily from you guys. I'm looking for some ways, I'm looking to see how you guys interpret the problem. So when I write the problem ambiguously, which is how the problem stated, it's very ambiguous. I expect, and part of what I'd like to learn from you guys is how you, the students, read these problems. And how do you interpret it? Now, I could have stated this problem much more specifically. I could have said, determine integer solutions, or show that there's more integer solutions. There's lots of different ways that I could have done this. But what's more sort of a learning experience, not just for me, but I also think for you guys, is for us to think of it this way. I mean, there's 4 or 5 different ways you can interpret this. Zafalgar, you've had a couple different interpretations that are in some ways similar to mine, but in some ways they're different. And I would hope that all of you who've given this a thought or thought about this problem have sort of, now whether you thought about it the way I did or not doesn't matter. What's important is, that you compare and contrast your interpretation of it versus mine. That's the learning experience. Now, one of the things that we have to get most of you off of is most of you are so trained to say, what's the answer? What's the answer? Is this correct? Is this correct? How do you do it? How do you do it? And oftentimes you guys don't want to take the time to step back and think and look at a problem from multiple perspectives. And then once you have thought about it for multiple or from multiple perspectives, multiple angles, you start to see how many things are actually the same. And so that's sort of what I'd like you to get from a problem like this. Not that there's just one and only one way to interpret this thing and is this the correct answer, because there's not. I stated this problem ambiguous on purpose, and the hope is that you guys learn something from that, if not on your own, but by sort of thinking about this. And so now there's also this new thing, if you're interested, and these Pythagorean triples are really fascinating. There's a lot to be read on the internet about them. And if you're curious, there you go. And sometimes we call these special right triangles. 3, 4, 5 is one of them. Okay, so that's pretty much all I wanted to say sort of about this. So if you have any questions about homework 3, now's the time to ask. Otherwise, we're going to sort of move on to newer things. Any questions, comments, concerns? All right. So let's get it going. All right. Here we go. Time to do math. So, let's, after homework 3, which is a sort of what I'd like to say soft intro to proofs, it's time to be a little more rigorous with these things. So we told you since day one that this class was about introducing you to proofs. It's also about introducing you to some different branches of mathematics that most of you are unfamiliar with, or maybe just have a small bit of familiarity. And so that's what we're going to do. And so we're going to start today with one of the more fundamental ideas in all of mathematics and its applications is what's called a set. So that's where we're at. So you've all, especially those of you, I should say, I will assume that you've all, at least in the English language, have used the word set before in many of its different contexts, I'm sure. Sort of the colloquial, or one of the colloquial ways to think about the word set is a collection of things. So we want to sort of use that idea. I don't want to say in particular, but when I stand up, I can't sit. It's very difficult for me to sit. So we want to start thinking about how do we make these sort of notions precise. We have an intuitive idea of what a set means from just English, but we want to have a mathematical idea. So here we go. So a set is an unordered collection of objects. That's it. That is the definition of a set. So you can imagine a set can be anything. It can be numbers, and that's going to be very common for us in a math class. It can also be other things. It can be a collection of letters. It can be a collection of words. It can be a collection of, cars. It can be a collection of anything. So we call the members of a set the elements of the set. So you'll see the word elements and members used a lot. So we're very used to doing things with symbols. So it's convention to denote a set with capital letters. And I'll go back in a second if you need. And its elements with lowercase. So, yeah, I'm going to head back, Mackenzie. Give me a second. Now, you've been working with sets sort of your whole entire math career and in other classes too. When you guys were in math class, we typically talk about, like, as we sort of even said this on Monday without explicitly saying it. We talked about things like, hey, this is the natural numbers. These are the real numbers. These are the rationals. Does anybody have a question? Okay, so what are some other conventions? It is also convention to use brackets when writing the set out. So let's do an example. Just going to make a set up. So we might have the set A, which could be, let's say for fun, it is the even positive integers up to 10. 2, 4, 6, 8, 10. Maybe we have another set. Instead of numbers, it's, how about the vowels? A, E, I, O, U. And I guess sometimes Y. Maybe another set is pets. How about cat, dog, fish? And then, of course, we have other sets that you are familiar with. We already defined this the other day, the natural numbers. Or did we not define? I think we did. The natural numbers are 1, 2, 3, 4. And, of course, the idea is that those numbers go on forever and ever and ever. Does anybody have a question about this? So there are 4 sets. One I mean, again, you're familiar with all these, I think, but we're going to write them with these brackets. Let's look at the next page. And please tell me to go back if someone needs to be caught up on this. Now, we also talked about the rational numbers. We talked about, well, let's sort of go in order. The first one we did before that was the integers. The integers are, let's say, how do we illustrate that there's a pattern here? We use these ellipses. And those ellipses tell us that that pattern extends indefinitely in both directions. The rationals, this one was tough. This was the set of all quotients, P over Q, where P and Q, excuse me, P and lowercase q, are integers, and there is one subtlety, is Q cannot be 0. So as I said on Monday, you know, when you see something like this, and again, some of you have seen this notation before, others haven't. This is called set builder notation. So if you haven't seen it before and you want to sort of brush up on it or whatever, then you could just Google that. Or a good way to learn this, as I mentioned on Monday, is to sort of think of those brackets to say the set of. And then when you look at this last one, the way you might want to read this, this is the set of all P divided by Q such that P and Q are integers and Q is non-zero. We can even have a set of a set. As you guys know, you can list, for example, you could say, I'm going to have a collection of sets. So what do I mean by that? Well, what if we called the set C, suppose C was the set of the natural numbers, the rational numbers, and we'll even put a boldface R. So for those, I know we didn't maybe define this yet here, R is the real numbers. Does anybody have a comment or a question? Okay, so the last few pages, what's the point to take from this? The point is, anytime we have a collection of objects, the mathematical definition for that is a set. Each item in this collection is called an element or a member. We, by convention, use these brackets to express that something is a set. All right, now we need a little bit more sort of notational conventions. So it's convenient to write lowercase a, and then I'm going to put this little letter here. It's almost like a backwards 3. And what this means, whoa boy. This means that A is an element of capital A. So this little symbol right here, that just means is a member of or is an element. Or for shorthand, you could say little a is in big A. So let's just look at a simple example of that. Let's say big A is the numbers 1, 3, 7, 9, 11. Then it's okay to say 3 is an element of A. So there's useful thing here. There's a negation of this. So if A is not in capital A, we write A and then we put a slash through this. That's how we negate it. So notice if I come back to here, I might write 5 is not an element or not in A. Because as I've described A, it's 1, 3, 7, 9, and 11, but 5 is missing. Does anybody have a question? All right, now the next thing we're going to talk about is kind of usually, it doesn't make sense to us at this level. You're like, what do we need it for? But it turns out there is a set that has no elements. Now, again, it's hard for students to appreciate the need for this the first time you encounter it. So, you know, you're going to have to come to terms with it. It's going to be confusing to you. But there is a set that has no elements. You know, you can imagine this. You might have a drawer in your shelf at home that doesn't have anything in your drawer. So that sort of bin is empty. So because of this, so we call this the empty set because it's empty. And we denote it by the Greek letter, which looks like this. Well, I guess I shouldn't. Really, it's not the Greek letter. I'm sort of lying. It's like a 0 with a slash. It's like a big 0 with like that. Does anybody have a question? Comment? All right, so the obvious thing we'd like to talk about then, and if you're thinking ahead to things that you're familiar with already, like think about for most of you have had algebra and calculus before. So when you're in, say, a calculus class, what are you doing? You're talking about these functions, and typically these functions go from one interval, and you plug it, we usually talk about it's continuous on this interval, or it's differentiable, or we're integrating over an interval, excuse me. And so it's important to understand that we need to sometimes distinguish when something is a part of something bigger. And so the terminology that we're going to use there is what is called subsets. So it is important to, or so not say important, but it is useful to define a subset. So we say A is a subset of B. And write A sort of like a sideways U with a straight line under it. So what does it mean? What is the definition of being a subset? Well, this is if every element of A is also an element of B. So, it's kind of useful to put this in terms of symbols and connect it with your stuff that you know from before. So in symbols, we say for all x, x being in A implies that x is also in B. So more specifically, this thing has to be true. Now, I'm not saying that one way of doing this is better than the other. So what I mean by that is students, when you're amateurs, when you're beginners like you guys are, what I've written in purple, this symbolic definition, or I guess technically the way you want to say it is, this is sort of a translation in the symbols of the definition. That is usually difficult for us to sort of grasp. We're usually at this level better at doing the English portion of this. Saying that a subset A is a subset of B, excuse me, if every element of A is also an element of B. That's correct. Now, Ethan, that's a good point. So Ethan says all elements are A or in B, but not necessarily the other way around, and that's correct. So we will distinguish that later. There's what's called a proper subset. But what we're leaving here, an equivalent way of thinking about this, Ethan, is sort of think with numbers, less than. When you have order in numbers, you have less than, but you also have like less than or equal to. So for example, 3 is less than 4. But I could write 4 is less than or equal to 4. That's not wrong. It's just a silly way to write something. So you might ask then, why is it defined this way? Well, it's defined this way because there are times when a subset is in fact the larger set itself. And we'll see that many, many times going forward. So there's a good way to visualize this, and this might help. So there's these things that some of you may have seen in school before. They're called Venn diagrams. Writing for all. So that might be something you want to Google and read if you haven't maybe done it before. But Venn diagrams are nice. So for example, we might say, here's our bigger set, B, and then our set A sits inside of it. So let's just take a point. Suppose I call this point X. So note, X is in A, and X is in B. But if I take a point over here, let's just call it Y, here, Y is not in A, but Y is in B. So if we want to use a more number sort of using numbers, we might say, okay, let's take the set of all rationals. We know that the integers are inside of them, and then inside of the integers are the natural numbers. So in terms of subset notation, we would say the natural numbers are a subset of the integers, and they are a subset of the rationals. So look, this kind of stuff is not easy to learn. It takes a lot of time and effort. And the word that I often think is great to use with trying to understand a lot of this is the word persistence. A lot of times you're going to feel lost and stuck. That's part of learning this that's part of the process. I know you're going to say, I don't want to hear that, but unfortunately, I got to tell you, that's what you got to do. Does anybody have a question about this? Comments? Does that make sense, Ethan? I don't know. So let's put a remark there. It's worth noting out. So the notation A subset B leaves open the chance that A equals B, or that they're the same set. So let's make sure we understand what that means before we go any further. we say two sets, A and B, are equal if they have the same elements. Now, what's fascinating, this is equivalent to two things. It's equivalent to A being a subset of B and B being a subset of A. Now, there's our first theorem is quite important, and it helps illustrate a couple things about this notation. And I'm not saying it'll illustrate it to you right away, guys, but I would ask you to think about it. And I would also ask you to try to prove this on your own. So here's our first theorem about sets. There's two pieces to this. So let me sort of phrase it this way. Let A be any set. Then two things must be true. Then, number one, the empty set is a subset of A. And number two, A is always a subset of itself. Now, you might say that's ridiculous to say that A is a subset of itself, but it turns out that saying it that way becomes very advantageous in many places. So you kind of have to trust us that the correct way, even though it seems sort of silly to say that 5 is less than or equal to 5, or even though it seems silly to say that 22 is less than or equal to 22, and even though it's silly to say that the natural numbers are a subset of themselves, it turns out that there are many times when it's useful to have that vantage point. You know, just imagine the analogy when you're in a math class. It's nice to have this, say x less than 4. Well, we know the solutions to this aren't just everybody less than 4, but also 4 is included in here. So these two sets mean two different things. And so we have to keep that in mind when we think about these definitions, because when we write something like what I'm writing right here, you might think at first glance it means it's being silly, but it's actually quite useful to have. Now, you should go through the proof. Maybe I'll assign it as homework. I don't know. But we're not going to do that proof together. But this also inspires a definition, and this maybe hits on your point, Ethan, from your question earlier. So if A is a subset of B, and we want to emphasize, or I shouldn't even say want to emphasize, let's just say it, let's just define it sort of in the following way, but they're not equal. We sometimes call A proper subset of B and right, as you might expect A subset B. But this, without the horizontal bar under this sort of creature right here, without this horizontal bar, that means it's a proper subset. That means we know for a fact A is not the same thing as B. Does anybody have a comment, question about this? All right, so let's take a moment to sort of think about what we've been doing. We're saying in a math class, we're interested, and this is a big theme in math, we're interested with working with certain things. In calculus, we worked with real numbers and functions on real numbers. But we can really generalize that to say that we're working on the set of, say, continuous functions, or the set of differentiable functions, or the set of functions, you know, without having any restrictions on them. In this class, we're going to work a lot with what we call discrete mathematics, which, again, we're going to be working with different types of sets. And so we need a solid sort of foundation with these ideas. So once we talk about sets, the next maybe natural question that someone might have is, what is the size of a set? So what we can do is we can quantify that. So if A has n distinct elements, it is called finite. So it's clear what I mean by this. Clearly, n must be a positive integer. And here's a fancy word. We call n the cardinality of A. So the best way to make sense of this is to just, and by the way, I guess we should give you the notation. We write A with the vertical bars, almost like an absolute value sign, which is another common theme from different sort of disciplines in mathematics. So let's just show you exactly, get right to it. Don't stress over this fancy word cardinality. It's not going to bite you or hurt you or anything like that. Okay, so let's look at an example. So let's suppose A equals the set 2, 4, 6, 8, 10. Well, the cardinality of this is how many elements are in it. There's 5 of them. Let's look at the one we did before. How about this? 1, 2, 3, all the way up to 23. How many elements are in here? Well, there are 23. So the notation we use is B with these vertical bars. Does anybody have a question about this? Why is it 5? How many elements do you count? Duh, exactly. Yeah, we can even do our silly pet one. What was our pet one? It was like cat, dog, fish. How many elements are in here? 3. All right. So, and then of course, if these guys are finites, what happens if this isn't true? So if it's not true, we say it's an infinite set. If A is not finite, we call it infinite. So again, this is a very, these words that you've heard before, they seem to fit the bill here. All right, so once we know the size of a set, that's good. And then, of course, just like think of the themes you've done in all your other sort of math classes. You don't realize it, but when you're in like algebra, you say, let's learn about this. Oh, and then like, oh, if we have a bunch of these things, we can build new things by combining the old things. And so sort of the question you might ask is, how do we make new sets from given sets? So we can sort of create new sets from our known sets. Whatever that means, known. So the most basic example of this is what's called a power set. So let A be any set. All of the all of the subsets of A form a set. We call this new set the power set of A, and denote it by, we typically use like a script P, parenthesis A. So let's do an example real quick to sort of help illustrate this. I think examples are the best way to sort of see this. So let's take our English example. So let's say we have some set C, which is cat, dog, fish. So what is the power set? The power set of C, well, let's write it out. What's the first element in the set? The first element, remember, this empty set is a subset of everything. And then what's the next element? Well, it's going to be just the set cat. Then the next one is just dog by itself. And then fish. Okay, then we have to sort of, okay, what else do we have? Well, we have cat and dog. That's a subset. We have cat and fish. That's a subset. And then we also have, we haven't taken dog and fish yet, so we have dog and fish. And then last but not least, we have the set itself, which is cat dog, and fish. So that is the power set of C. So here's a cool thing you might guess if you practice these. We'll prove it later. Here's a cool fact. Try to see if you can prove it now. So if the cardinality of C is equal to n, then the power set of C equals 2 to the power n. So for example, in this problem, how many elements did C have? It had 3. Notice that there are 8 elements, 2 to the power 3 in my power set. Anybody have a comment on this question? All right, so how else can we build sets then? Remember, right now we're saying we start with some set, how do we build new ones? So another way that's familiar to you, although you don't really think of it this way, it's probably not been sort of thought of this way, but you've done it. So another way to create a new set is to use ordered pairs, or the fancy word for this is the Cartesian product. So if I give you 2 sets, given A and B, we define their Cartesian product by the following way. So it's a new set that we write A sort of multiplication sign B. And what is this? It is the set of pairs A comma B such that little a is an element of big A and little b is an element of big B. So here, this is an example. You've actually used this many times in your life. You just don't know it yet. So note, if A and B are the same set and they are R, the real numbers, then R cross R, which we often denote as R squared, is the plane that you know from algebra and calculus. Any of you who've had calculus 3, you'll have learned that there's, instead of just doing A and B, two guys, you can do 3 and you get 3-dimensional space. So there's all kinds of cool things you can do with this. And so you can build new sets from old sets, is what we're saying. Does anybody have a comment or a question about this? Any comments or questions? So you can actually do a Cartesian product with more than 2 sets. You can do it with 100 if you want it. But we'll get to that if necessary at some point. Anybody have a comment or a question? All right, I think that's a good place to stop. So we will, I'm going to post an assignment. Hopefully you guys start reading these notes a few times and making sense of it. And then we'll go from there, and we'll talk more about this stuff on Monday. Does anybody have a question or a comment? All right, then. Well, I will call you. I will see you guys next week. Thank you very much, and hopefully you learned something. Take care, everybody.